What's up, everyone? I'm back again. So I saw the comment basically saying that I should be more prepared so the pace of the video doesn't get slowed down by me sitting here thinking about what I want to say next. I thought that was a good comment. I appreciate the feedback, and I thought about what I wanted to present in this video. I will say I think the beginning of the video might be a little bit less structured just because I want this to serve as sort of a journal of what I'm working on recently and what I'm thinking about recently. And so maybe I'll spend the first couple minutes or first few minutes just reflecting on what's going on with my work and my research and my classes. And then I'll have something that I want to discuss in the preceding, coming after that, rather. And also if you want to say, give me feedback in the comments, or maybe tell me about what you do and don't understand, or what you do and don't like about these videos, let me know. I'll take that feedback into consideration, definitely. So I appreciate that. So the term has finished about a couple weeks ago. I wanted to make a video sooner, but I was kind of taking a break. This last term I was really I guess tired just with classes. So maybe a bit about me. Like I mentioned in the last video, I'm a PhD student, technically in civil engineering. My focus is on ocean and coastal engineering. Specifically, my research involves wave theory and ocean waves and the sort of analysis of that. I think most universities have this degree as mechanical engineering because it's like fluid dynamics. And then I'm doing a master's in math as well. And so my research is very mathematical, and I really enjoy math just on its own. So hopefully I can give some insight and maybe just some of the interesting mathematical phenomena going on within some of these physical problems. But yeah, I've been tired at near the end of these more recent terms just because I've been taking so many classes. I have to take 45 credits of graduate level math classes on the back of having taken my course load for my PhD program. So I'm just sort of getting class burnt out. I'm near the end of my credits for my math classes. I think I have two more classes to go. So I just finished complex analysis, which was great. A lot of the theory in the analysis of ocean waves involves complex analysis, or there's complex analysis in the background. And then I finished Ocean Structural Dynamics, which was taught by my advisor, which was also a really great class, and allowed me to kind of work on my research as part of the coursework, which was good. I did a big course project on something involving my research and simulating wave energy converter motion due to wave action pushing against the wave energy converter. So that was good, but yeah, so it's summer term has just started, I think, officially today. I'm not taking classes in the summer, I'm just doing research, so that's going to be great. Just kind of focus on getting some research done, hopefully getting maybe a paper out this summer, but maybe more on that later. So why don't we start with what I wanted to talk about. So I wanted to start maybe by a brief introduction of eigenvalues. So, and eigenvectors. So essentially, just, simply put as possible, if A is a matrix and V is a vector, then V is an eigenvector if when A acts on it, we get the vector back multiplied by some scalar. Then that means that V is an eigenvector. And these are really important in physics and engineering, and even, I mean, math, obviously. And A here is a matrix, but A can be anything that, what we call as a linear transformation. So linear transformation, what is that? Essentially, so we call linear transformations T, usually, or A for a matrix. We use capital letters for matrices, and T for transformations or linear transformations. So if T is linear and X and Y are vectors, then Tx, it distributes over vectors, the summation of vectors, and let's say that T acts on some vector C times X, well then this is equal to C times T of X. So these are the properties that characterize a linear transformation. And it's of interest to find out what the eigenvectors of a linear transformation are. And that is really one of the ways we solve the simplest formulation of the ocean wave problem is by finding these eigenvectors, and our eigenvectors are sinusoids. So if you want to learn more about eigenvectors, if you don't know about them, there's a great video of 3 Blue 1 Brown on YouTube. Has a great introduction to like eigenvectors and what they physically do, and how they're, what happens when you operate on vectors with matrices, and what happens in the special case that the vector is an eigenvector, and that's very interesting, so check that out. So the equation I solve is the gradient squared of phi equals 0. Now phi is a velocity potential. I guess you can think of that as like a potential energy, a representation of the potential energy in the fluid. And the gradient just tells you to take the derivative in the spatial directions. In the water wave problem, the simplest version is that we have a so if we're looking at the fluid from the side, in and out of the board, the behavior is exactly the same as in this plane. And so we really only need to analyze 2 spatial directions. And so this phi function, this velocity potential, is a function of x, z, and t. So we have x, z, and if we're fixed at a single spot, well, we can imagine if we're on the surface here and we're fixed at a single x and z spot, well, that behavior is going to change in time. So now, this gradient, which is the spatial derivatives, I'll write that out here. Rather d. I have to say, you never appreciate just how hard it is to give a lecture until you've tried to give one. So phi dx squared plus d squared phi dz squared. So this. So let me just erase this. So these are the same equation. This is just writing it out more explicitly, and this is just how we normally write it, just compactly here. And this is what we call it's a Laplace equation or the Laplace equation. I guess I would say a Laplace equation just because it maybe depends on what function you're applying. Although all the functions should have the similar property. They should be holomorphic or satisfy what's called the Cauchy-Riemann condition. So that's something involving complex analysis, and it's sort of in the background of what's going on here. And I guess you can maybe, if you know complex analysis, you can sort of see from this form here how this function might satisfy the Cauchy-Riemann condition if it's a holomorphic function, just because we have these two directions here and they're equal but opposite. So anyway, so back to eigenvalues. So this is a linear operator, and so we can find these eigenvalues here, or in eigenvectors, and essentially, with a little bit of mathematical handiwork, we get these eigenvectors, and really what we can think of them as being are, so if we're given the surface over time, the water's surface, we can think of those eigenvectors as being the sine functions which when summed together equal this surface. So you might have heard of Fourier analysis, where you can represent this smooth function as a summation of sines and cosines. Well, essentially we do that to this water surface, and it just so happens that the eigenvectors, these sinusoids, are the components that sum together to equal this surface. So we call this surface eta, and it varies in x and t. The reason it varies in x and t is we're technically at z equals 0. Now, one of the assumptions we make is that the waves are of small amplitude. So even though we're not quite at 0, we can, mathematically we say, well, we're at 0. So that's why z isn't appearing in this. And this is equal to a sum of sinusoids. Really, I guess we... Yeah, so, well, yeah. Kx plus omega t plus phi. Where omega here is the frequency, k is the wave number, and phi is an initial phase. So phase, so if we're on a circle, let's say we start here, at time equals 0, we're here, so at time equals 0. Well, then we need to specify this value so that our sine function sort of has this initial size, right? And so that phi value is just where we're starting on the circle. And so each of these individual components actually will have various wave numbers, various frequencies, and various phi values, the phase, initial phases. So that's great. These are the eigenvalues. And the nice thing is these are invariants. Now, in physical systems, one of the best ways that you can understand a physical system is by finding its invariants. So I'm sure people have heard of the principle of conservation of energy. And so invariants are things that are conserved as these functions change in time. So even though we might travel in space and time in this, it's still represented by this sinusoidal function. And so that sine function is invariant. Just like energy is conserved, these sine functions, even though this wave might look different at different times in different locations, it's still represented by the same functions, the same summation of functions. And that's great. So having these invariants are really important because they give us something steady to hold on to when we're analyzing the behavior of the system. And one of the interesting things is these invariants, these eigenvectors here in this case, are invariant, as in they don't change, under what's called the Fourier transform. So with the Fourier transform, so this is a physical representation of our wave surface. Well, let's say that this is time, and this is displacement. Well, actually, this would be eta. not x. And so this is a point, and it's moving in time like this, and it's composed of all these sinusoids. What we might want to do is we might want to transform this to understand how the energy of the system is distributed among these frequencies. And what we do is we can apply a Fourier transform, which will give us, so this is power, and this is frequency. Maybe I don't need to make it so long, but this is frequency. And we'll get this spectrum. Now this spectrum, the height of this is telling us how much power is located at some frequency value. And so each of these sinusoids is moving at a different frequency. And so when we transform them, the sinusoids are sort of preserved, but they're just represented in this different way. And this allows us to determine how this energy is distributed over time. Now, what we would call where the location of maximum energy, we call that the peak frequency. And there's all these sort of interesting properties. We really typically work with the spectrum, and there's all these sort of interesting things you can say about the spectrum. So in my case, we're looking at the ocean. Well, one of the interesting things that we can do, so one of the measures of that we might want to produce in data is what's called the significant wave height. So we might want to get an understanding of, well, historically, the significant wave height, hundreds of years ago, I think it was the British Empire would tell captains to stand on the, at different times of the day with their logbook, they would stand on the bow of the ship or the stern of the ship or whatever, and they would look down at the ocean, and they would sort of measure the tallest 1/3 of the waves. And so it's called significant wave height because it's significant enough for you to be like, oh, I want to note that down in my book. And so this term significant wave height became historically prominent because the British had asked their captains to write this down in their logbook and had this sort of characterization of waves all over the earth. And anyway, so that term has been used, and there are a couple of different ways that it's used. There's actually two distinct ways that it's used in my field, and it kind of leads to some confusion. But anyway, significant wave height is sort of like, it's basically about the tallest, it's the average of the top 1/3 of waves, their heights. So it's a way we characterize seas, and if it seems confusing to you, it's confusing at the start, but it becomes very useful as you analyze data and get a feel for what it means. Anyway, so back to this spectrum. Now, the interesting thing is that the significant wave height can be directly produced from the spectrum by integrating. So there are what's called spectral moments, which I'll write down the equation for them here. So M is for a spectral moment, I is an index, so it just tells you which spectral moment you're finding. And then mathematically we would say it goes from infinity to negative infinity to infinity, we just want to get the whole spectrum in there, really. And then it's F to the I S X X df. So this just means we integrate over this function, and we may multiply by this frequency vector as a sort of scaling. Now, the significant wave height, which we would write as Hs, is is equal to 4 times the square root of the 0th moment of the spectrum. So the 0th moment, so we just put 0 in here. F to the 0, so that's just 1 df. So it's just integrating, it's just this area under this curve here. And so just from the area under the spectrum, we can get an idea for how big our C is. And there's a bunch of parameters using different moments of the spectrum that give us different information about the C. And it's really all comes down to these eigenvectors that that are invariants for our equation, that are sort of preserved under these things like the Fourier transform, and allow us to characterize our data in different ways. So that's really what I wanted to talk about today. So I hope people got something out of that. If you made it this far, feel free to leave a comment and tell me what you did or didn't like about that presentation, maybe something you didn't understand, or things you'd like to know more about. But yeah, that's it. Thanks for watching.